Assalamu alaikum and welcome to lecture number 10 of CS218 Data Structures and Algorithms. The topic of this lecture is linked structures and we use chapter 6 of book 1 for this topic. Things that we know about arrays and lists. Let's go over them a bit. An array provides easy and direct access to the individual elements, but it is limited in functionality and has a fixed size. The Python list is implemented using the C array. The Python list has a larger set of operations than an array and can adjust in size as items are added or removed. The array and Python list can be used to implement many different abstract data types. Binary search can be used with both structures when items are stored in sorted order to allow for quick searches. But there are disadvantages of arrays and lists. Insertion and deletion. Insertion and deletion require items to be shifted to make room or close a gap, which consumes time. Changing size. In the Python list, expansion requires the creation of a new, larger array into which the elements of the original array must be copied. This takes considerable time. Memory allocation. Array elements are placed contiguously in memory, so we must find a block of memory large enough to hold the entire array. For large arrays, this can be difficult. This is especially true for a Python list since expansion requires even larger blocks of memory. So this motivates us to look for other data structures, and the first one we come across is the singly linked list. The singly linked list is a structure composed of nodes. Each node has an info field and a next field. The info field carries the data item that needs to be stored in the data structure. The next field contains a pointer to the next node of the singly linked list. So this is a node containing 56. It points to a node containing 23, which points to a node containing 12, which points to a node containing 64, which points to a node containing 85. The pointer of the node containing 85 is none. This means that the node containing 85 is the last node of the singly linked list. The entire data structure can be accessed via a head pointer. So what I have in my hand at all times and what makes me able to access the singly linked list is the head pointer. Anytime that I want to read this list, I start from the head pointer and then I move through the pointers. So now I am reading the list starting with the head pointer 56, 23, 12, 64, 85. A pointer is the address of an object. In Python, it is also called the identifier of an object. The linked list data structure can be used to store a collection in linear order. Now I want you to look at something. You see a boy. You ask me for the location of the boy. If I place an arrow here, I am not giving you the location of his arm. I am giving you the location of the boy, or I can place the arrow here. Again, I am not providing the location of his shirt. I am providing you the location of the boy. Or I can place the arrow here. This is not the location of his jeans. This is the location of the boy himself. Now look at our node. You ask me to give you the location of the node in memory. I place the arrow here. This is not pointing to the info field. This is pointing to the whole node. I place the arrow here. Again, I am not pointing to the info field or the next field. I am pointing to the node. Or if I place the arrow here, I am not pointing to the next field. I am pointing to the node itself as a whole. So this brings us to this conclusion. A pointer points to the whole object, not the fields or elements inside it. Now I have created a class called listNode for the nodes of a singly linked list, and it is placed in a file called singlylinkedlist.py. Let us first look at the init function. The user gives us some data that he wants us to store and pointer to the object of this class called self. The first line says self.data is data. So this is self, and what we are doing in the first line is that we are placing data in the info field. Now let us look at the second line. In the second line, we have put none in the next field of self. Why none? Because this is the only node in the list and there is no node after it. This takes us O1 time because both lines in the init function are constant time lines. Let us look at the insert function. The insert function inserts a node after the node pointed to by self. So suppose that you have this singly linked list and self is here. Self is pointing to the node which contains D. What do we want to do? We want to insert a node containing value after the node that contains D. So the final picture should be that there is a node containing D, then there is a node containing value, and then there is a node containing A. This is what we want. Look at the first line of the insert function. It says n equals list node value. So this line called the init function that we just saw, and it made a node and it placed value in the info field and it placed none in the next field and it named the pointer to this node as n. The next line says n.next is self.next. What is n.next and what is self.next? Let us see. This is n.next and this is self.next. When you say a pointer is equal to another pointer, you are trying to say make the pointer on the left point to the place where the pointer to the right is pointing. So if I read this line in this way, I will say make n.next point to where self.next is pointing. Self.next is pointing to the node containing A. Again I repeat, the line says make n.next point to where self.next is pointing. Now n.next and self.next are pointing to the same place or the same node. Read the next line. Self.next is n, or make self.next point to where n is pointing. You already know where self.next is, and you can see where n is pointing. I want self.next to point to the node where n is pointing. Now self.next and n are pointing to the same node which contains value. Let me rearrange the picture for you. Now do you see that the node value has come between the node containing D and the node containing A? Or I can say that the insertion is complete. This code has inserted the value containing node after the node pointed to by self. If I ask you for a complexity analysis of the insert function, you will say O1 because all lines of the function are constant time lines. This is the delete function. The delete function deletes a node after the node pointed to by self. Keep in mind that it deletes the node after the node pointed to by self, not the node pointed to by self. Why do we delete data from a data structure? When I was talking of data structures in lecture 1, I told you that data structures are containers for data, like your wardrobe is a container for your clothes. When you take clothes out of your wardrobe, you are doing this because you intend to use them. So I can say that you are retrieving clothes out of the wardrobe, or I can say that you are deleting clothes from the wardrobe. Likewise, when a user asks to delete data from a data structure, the user wants to use the data structure. So during the process of deletion, we first copy the value of the data structure to be deleted in a new variable, and then we delete the data structure, and then we return this new variable to the user because he wants to use it. If you look at my code, there is a variable called item, and at the end of the code I am returning item. This is the variable in which I will place the value of the deleted node, and at the end I will return this variable to the user because he wants to use it. So let us consider that I have this singly linked list, and this is self. Self is not pointing to the next field of A. Self is pointing to the whole node containing A. When I start the delete function, item is none. There is no value in the item variable. The if condition says if self.next is not none. So what is self.next? This is self.next. Is the if condition true? No, the if condition is false. Self.next is none. So we skip the body of the if. We come to the last line and we return item which is none. What does this mean? If you look at the singly linked list, you will see that the node containing A is the last node. Our function was meant to delete a node after the node pointed to by self. But the problem is there is no node after the node pointed to by self. So since there is no node to delete, the value of item is none. And this is what we return. Now, when the if condition is false, this is the best case of the function because you execute only three things. The first line, the comparison, and the return statement. And this is an O1 complexity function. But what if the if condition is true? Let us say I have this singly linked list. I am looking at the last part of the singly linked list, the three last nodes. There is a node containing D, then a node containing B, then a node containing A. And self points to the node containing D. So this function should at the end return B and delete the node containing B. Let us see if it does that. First of all, item is none, and then we determine self.next, which is this, and then we execute the if comparison. If self.next is not none, the comparison is true. Then the line says TMP is self.next. We know what self.next is. This line is trying to say take a new pointer TMP and make it to point where self.next is pointing. Self.next is pointing to the node containing B. So TMP should point to the node containing B. Item is tmp.data. What is tmp.data? B. So this should be placed in item. Done. Then there is a line saying self.next is tmp.next. Make self.next point to where tmp.next is pointing. Where is tmp.next? tmp.next is pointing to the node containing A. This is what I do. Self.next is pointing to the same node to which tmp.next is pointing. Now see, tmp is a variable which exists within the delete function. So when the delete function will fall out of scope, tmp will also perish. It will fall out of scope. Let me rearrange this picture. TMP is pointing to the node B, which is pointing to the node A. But look at the singly linked list. D is pointing to A. Is any node in the singly linked list pointing to the node containing B? No. So can I say that the node containing B is not a part of the singly linked list anymore? Yes, I can say that. So we have effectively deleted the node containing B because no node in the singly linked list points to it anymore. And when the function will fall out of scope, both TMP and the node containing B will fall out of scope. So the last line is return item. Item is returned. TMP falls out of scope because the function has completed. And since nobody is pointing to the node containing B, B also perishes because a node can only be found if somebody points to it. If nobody points to a node, you can never get to that node. So that node ceases to exist. There is a garbage collector in Python interpreter, and when it sees that nobody points to a particular node, it wastes that node or it deletes that node or the node perishes. So this is what happens. And this is our final picture. So we can say that this is the worst case of the function, because in this case all lines of the code are executed. Again the function is O1. In the delete function, you saw that it deletes a node after the node pointed to by self. So the pointer self was at the node containing D, and this was the beginning. And then in the end, what we deleted was not the node containing D, but the node containing B. So this means that for deletion, we require the pointer of the node before the node that must be deleted. If we want to delete, we must have pointer to the node before the node that needs to be deleted. Do keep that in mind. Now we look at the len function for our class list node, and you know that the len function gives you the length of a data structure. In our case, it will give us the number of nodes in the singly linked list. What we will pass to the len function is pointer to the first node of the singly linked list. So this is our singly linked list, and self points to the first node. If self points to any other node, then we will not be able to count the nodes before self. So that will give us an inaccurate number. So the code says A is self. Make A point where self is pointing. I equals 0. I is a variable initialized to 0. While A is not none. So check, is A pointing to none? No, it is not. We move into the body of the while, which says increment I. So let's do that. And then it says A equals A dot next, or make A point to where its next is pointing. What is A dot next? This is it. A dot next is pointing to the node containing B. So A should point there as well. One iteration of the while done. Go back to the condition of the while. A is not none, that is correct. I plus equals 1. A equals A dot next. Where is A dot next now? A should point where A dot next is pointing. A dot next is pointing to the node containing C. Second iteration of the while loop done. Go back to the condition. A is not none. Yes. I plus equals 1. Where is A dot next? Make A point to where A dot next is pointing. A dot next is none. It is not pointing to anybody. So this line will have this effect. A will also become none. The third iteration of the while is done. Go back to the condition of the while. A is not none, but this is false now. What do? You return I. I is returned. How many iterations will we do for the while? As many as the number of nodes. Let the number of nodes be n. I can say that the time complexity is O(n). Look at the traverse function for this class. I have this singly linked list, a node containing D, then a node containing B, then a node containing C. Self points to the first node. The first line of the traverse function says A equals self, or make A point where self is pointing. So I do that. Then it says print traversing the list. So in the output, I show this line. While A is not none. A is not none. The while condition is true. Print A dot data and end it with a space. So what is A dot data? D. So I print D. A equals A dot next. Where is A dot next? A dot next points to the node containing B. A equals A dot next means make A point where A dot next is pointing. One iteration of the while is done. Go back to the while condition. A is not none. We have to print A dot data. So what is A dot data? It is B. We print it. Then we find A dot next and we make A point where A dot next is pointing. Another iteration done. Check the while condition. A is not none. Where is A dot data? Here it is. Print it. Locate A dot next. A dot next is none. So when you set A equal to A dot next, A will also become none. Go back to checking the while condition. It is false. You come out of the while. If you look at the output, we have printed out the values of the nodes of the linked list. Again, this function is on because the while will run as many times as the number of nodes n. Searching in a singly linked list. We implement a function to search for a data item in the linked list as a class function of the class listNode. This function returns a Python list of 3 elements. The first member of the returned Python list is true if the target of the search is present in the linked list and false otherwise. The second member of the returned Python list is a pointer to the node just before the node containing the target of the search. The third member of the returned Python list is a pointer to the node containing the target of the search. If the target is found in the first node of the linked list, then there is no node before it. So the second member of the returned Python list is none. We return the pointer to the node before the node containing the target to help a user who is looking for the target to finally delete it. Now we look at the search function that we have implemented. The search function takes 2 arguments, pointer to a list node object called self and a target value for which we have to search. So this is my list and this is self. And let us suppose that the target is D. The first line says A is self, or A should point where self is pointing. So we do accordingly. The if says if A dot data equals target. What is A dot data? This is A dot data. It is equal to target. What has just happened is that we have found target at the first node of the linked list. there is no need to traverse any further. So we move into the body of the if, and we return a 3-element list. The first element of this list gives us the status of the search. Have we found the target? Yes. So the first element is true. The second element gives pointer to a node before the node containing the target. But the problem is we found our target in the first node of the singly linked list. So the second element is none. The third element contains pointer to the node containing the target. Hence the third element is the pointer A. We return this 3-element list. You can say that this is the best case of the search function and it is O1 in complexity. But what if the target is not in the first node of the linked list? Another linked list, the self pointer. We execute the search function for this linked list. We are looking for C. So A should point where self is pointing. Where is A dot data? A dot data is D. Is A dot data equals to target? No. We do not move into the body of the if. B is equal to A dot next. What is A dot next? A dot next is pointing to the second node. B should point to the same place. Next we move into the body of the while loop. While B is not none, this is true, B is pointing to a node, and B dot data is not equal to target. So what is B dot data? B dot data is E, which is not equal to target. So the second condition of the while is also true. A equals A dot next. What is A dot next? A dot next points to the node containing E. A should also point there. B equals B dot next. Where is B dot next? B dot next points to the node containing C. B should also point there. So what we have done is we have advanced both pointers. Up till now you've seen this done many times. When we say A equals A dot next, we are moving a pointer to the next node. And the same thing happens when we say B equals B dot next. One iteration of the while is done. We go back to checking the condition of the while. B is not none. This is true. What is B dot data? B dot data is C. Is it equal to the target? Yes. So the second condition of the while loop becomes false and we come out of the while loop. Look at my picture. You say that A is pointing to the node before the node containing C and B is pointing to the node containing C. The next step is to return. Make a comparison. B is not none. This is true. So the first element of the return list is true. Then we have the second element, which is pointer to the node before the target node, that is A. Then we have the third element, which is pointer to the target node, which is B. We return this list. This is the worst case of the search. Why? Because we had to go all the way to the end of the list until we found the target. And we had to Go through as many nodes as there are nodes in the list. So the time complexity is O(n). A singly linked list contains the following elements in sequence: 1, 5, 7, 3, 8. Run the search function for target equals 6. Draw figures for all steps. Can this be considered the function's best or worst case? This is your homework. So what did we learn today? We were introduced to singly linked lists. We implemented a class to create and manage a singly linked list. We saw pictorial depictions of code fragments. And we found time complexities of all our codes. Things to do: read the book, note your questions and put them up in the relevant online session, and email your suggestions to me if you have any. Take care and Allah Hafiz.